We're now continuing on with talking about functions and derivatives. Let me just show you one more thing before we jump into the math. Here's a graph. If you're given this graph and you're asked to point out either the maximums or minimums, hopefully you would go here and you would say, right there is the maximum point. Okay, in a strict sense, it's a relative maximum, but like I said in the last video, I'm not going to keep saying relative all the time. We're just going to call this, here's the maximum point. In a minute, we're going to look at this function written as an equation. And we're going to be asked all kinds of questions about this. One of the questions are going to be basically find any maximums or minimums in this function. All right, so let me describe to you what's going on with this graph, because what we see at the graph is going to tell us how to approach this problem mathematically. I said this during the last video, but if we look at the slope, or I'm going to call the first derivative of this graph, the first derivative is positive here because it's increasing. When the first derivative gets here, when the slope gets here, you know, once again, we think about tangent lines. You can see at this point right here, this tangent line has a positive slope. So the first derivative is positive. But when we get to this one point, the very top, the maximum, if we were to draw the tangent line, we would see it's a horizontal line, which means m, which is the slope, right? The slope is 0, or the first derivative is also 0. Remember, slope and a first derivative mean the same thing. So what's going on? At this maximum point, the first derivative is 0. As a matter of fact, let me draw a second little quick sketch here. What if you're given this function and asked to find the max of the mins? Actually, there's a minimum here, and there's a maximum here. But you know what happens at both of these? If we look at the first derivative at these points, if I look right here, first derivative is 0, which means the slope is 0. If I look up here, at that point, first derivative is 0. This right here is the whole key to how we determine the maxes and mins if we're given a mathematical function. What we're going to do is we're going to take the first derivative and set it equal to 0, and we're going to solve this equation. And when you solve this equation, the solutions will be usually maxes or mins, although as we do it, you're going to see there's one more thing that can happen. But definitely, this is a way to find our maxes and mins. Maybe not every solution may not be a max or min, but the maxes and mins are definitely going to be the solutions to this. Let me give you the exception real quick, since I started to talk about it. Sometimes you may have an occasional graph where it comes down and you think it's going to be a minimum and it gets flat, but you know what it does? It stays flat for a while. And then it keeps on going down. So let's ask ourselves, well, what's the first derivative for this graph? Well, it's negative here. Here, it starts to flatten out. As a matter of fact, right in here somewhere, this function is actually horizontal. If we were to draw the tangent line, we would say right in here, the first derivative is 0. But then what happens? But then instead of coming up, it keeps on going down. It's like it flattens out for a little bit and then it keeps going down. So you know what happens here? The first derivative is 0 here. Now this point is not a max or a min. Normally, when the first derivative is 0, we have a max or a min. But occasionally, we can have a graph where it gets flat, where the first derivative is 0, but it's not a max or a min. So this is a little bit of an exception. So you'll see, we'll do some problems where to find our maxes and mins, we're going to do this. But every once in a while, when we do this kind of problem, our answer is not a max or a min, it's one of these. So that's just a heads up. We'll talk about this a little bit later on, and that'll be clear to you. But for now, the whole key, if we're asked about the maxes and mins, if we're asked about where is the function increasing or decreasing, where is the first derivative positive and negative, the answer to all these questions is based upon this right here. It's all based upon looking at when the first derivative is 0. Because what's going on here? The first derivative is 0 gives us a way to find these values of x. These are the points. These points really separate this graph. If you look at it, first derivative or the slope is negative here. We could say the function's decreasing. We get to this minimum, all of a sudden the first derivative is positive, the function's increasing. We get up here, all of a sudden the first derivative is negative, it's decreasing. These maxes and mins are when things change. Look at what's changed. The first derivative is negative. All of a sudden, the first derivative is positive. This was the point at which it changed. The function's decreasing, the function's increasing. Maxes and mins are where everything changes. As a matter of fact, these maxes and mins, and here, you know what the word we call this right here? I call this a neither. Because usually we're looking for maxes and mins, and sometimes you get one of these where it's not a max or a min, but the first derivative is 0. I call that a neither. These kinds of points are so important, we actually call them critical points. So oftentimes in a problem or in homework, you'll be asked to find the critical points of the function. The critical points means go find the maximums, the minimums, and occasionally you might have a neither. And you know how we find the critical points? Right here. You solve this equation. You take the first derivative and you set it equals 0, and you solve for x. And those x's are going to be your maxes or your mins or your neithers. Now, when we first solve this equation, immediately we don't know if it's a max or min or an either. We have to do some more work. But doing this, gives us their critical points. So we know those are the special points. Then we just have to figure out what those special points are. So at this point, I think we should just do some problems, and once you do a couple problems, I don't think you will find it terribly difficult. This is the whole key. I was going to write down the steps of how to do it, but you know what? There aren't really any steps. The steps are solve this equation. So let's go back. I wrote down this function a while ago. I'm going to go now do this problem. So let me rewrite this function. Here's a function. We're going to be asked multiple questions. First, they're going to say, find the critical points. And they're going to say, find the maximums or minimums. And I'm going to, right now, we could have an either, but just once again to save time, I don't want to keep saying max, min, and either. I'll just call it max or min, knowing that neither is a possibility. So I say find the maximum minimums. In this case, we're just going to find the values of x where either a maximum or minimum occurs. And then they say, then give the intervals where function is either increasing or decreasing. And then maybe just for fun, find the value of the function at the maximum and minimum. In other words, up here, when I say find the max and min, we're just going to get the value of x, where the max and the min are. Down here, then we actually go another step, and once we know where the maxes and mins are, they want to know what the actual value of the function is. So let's do these 4 steps. First step, first thing you always do is you find your critical points. To find critical points, solve first derivative equal to 0. So obviously, how do we do this? The first step is, here's our function. We have to find the derivative, the first derivative. Here's my function. Now we've learned all the rules to find the first derivative, so let's do it. Here I just have 4 functions, 12x squared minus 18x minus 30. That's the first derivative. You could think of this as the slope. Now what I want to do is, I want to take this first derivative and actually set it equal to 0, because when I do that and solve this equation, my solutions, or my values of x, are going to be my critical points. Those are going to be the special points on my function. Here I can see it easily because I can see the graph. Here all I have is an equation. I really don't know where the maxes and mins are. This is a way to do it mathematically. I need to solve this equation. Now this involves algebra. So how do I solve this equation? I have 3 terms here. This is a trinomial. You have to remember back to how to solve equations. What I'm going to do is, I notice 12x squared, 18x 30, 12, 18, and 30, I have a common factor of 6. So I'm going to factor out the 6. Now one of the ways you can try and solve this equation, here this trinomial, I can try and factor it. Matter of fact, If I divide both sides by 6, I have this. So now this is really the equation I need to solve. Now this is a trinomial. I'm going to solve this by factoring. You could use the quadratic equation, but whatever you want to do, you've got to be able to solve this equation. So the way I do it, I do the product sum. 2 times negative 5 is negative 10. The sum is negative 3. So I have to find two numbers that you multiply together that equal negative 10, but when you add them, equal minus 3. So this should be review for all of you. These are my two factors. If you multiply negative 5 and 2, it equals negative 10. If you add them, it equals minus 3. Now how I do this, to factor this, I rewrite the 2x squared, the minus 3x. I break it up into my two factors. Matter of fact, I'll put plus 2x minus 5x. So these two here combine to be minus 3x. So you simply copy down the first and the last term, and the middle term gets broken up into your two factors. And then at this point, you take these first two and you factor out the common factor. If I factor out the 2x, I have this. Then I take these two, and if I factor out a negative 5, and then you notice these two parentheses are identical, so we can factor out the whole parenthesis. And when you do that, we have now factored it, okay? So that should be review for you, hopefully. And now, to solve this, I take each of these parentheses and I set them equal to 0. Or another way to do it is you look at this first parenthesis and say what value of x would cause this whole parenthesis to be 0, right? Because 0 times anything is 0. This first one's pretty straightforward. Negative 1 is a solution. This one, it's not as obvious. Matter of fact, I may go off to the side and say, well, I need to set whatever's inside the parenthesis equal to 0 and solve it. Add 5 to both sides, divide both sides by 2. So I actually have two solutions. X is negative 1 and x is 5/2. What I've just determined are their critical points. For this function, way up here when I first wrote it, for that function, it looks like these two values of x are either going to be a maximum or a minimum, or maybe a neither, but probably a max or a min. Now, I don't know what these points are yet. I just know something is going on here, either a max or a min. I don't know what it is. So now the question is, okay, so these are my critical points. So when x is negative 1, what's going on there? When x is negative 1, is my function, is it a maximum or is it a minimum? When x goes to 5/2, which is the same thing as 2.5, what's going on there? Is it a maximum or minimum? I don't know. I need to determine it. So if you think about it, first step to these problems are find your critical points. So actually, let's go ahead. I could probably write down steps to solve these kinds of problems. We've done the first step. You know what the first step? Solve. Set the first order equal to 0 to find critical points. What's the next step? Let me think how I want to word it. I'm going to word it one way, and you see me do it, you'll understand how to do it no matter how I word it. I would say create chart to analyze critical points. In other words, this first step, we may know the critical points, but we don't really know what they are. We don't know whether they're a max or a min or an either. We don't know. Step 2 says, okay, here's how we're going to figure out what's going on at those critical points. So let me just quickly do a quick review of the problem we're in the middle of working on. Here was the original function. We took the first derivative, so I'm copying down what we've already done for this problem. Function, the first derivative. We've already determined our critical points. Turns out we have 2 critical points. One of them occurs when x is -1. The other one is 5/2. So this is what we've done so far. So now, let's do this second step. So here's what I'm talking about. It's almost like I do like an x-axis here. And I'm going to go mark each of my critical points. So in other words, if 0 is here, here's -1, and 5/2 is like 2.5. So here are my 2 critical points. And to make it clear, what I'm going to do is I'm going to draw these dashed lines, because what I'm really doing is I'm breaking up my graph or my number line into regions. Because if you think about the values of x, as you go this way, this is -infinity. As you go this way, this is infinity. I actually have 3 regions here. So the regions are separated by the critical points I found. So region 1, in a sense, we would say region 1 is when x is -infinity to -1. That's region 1. Region 2 is when x is between -1 and 5/2. And then region 3 is when x is larger than 5/2. Because here's what's interesting. Inside these regions, the first derivative is always the same sign. In other words, it's positive or negative. Inside the regions, the first derivative is not going to change. It's always positive or negative. The sign of the first derivative does not change. What I have to do is, in region 1, I want to go figure out, in region 1, say when x is -5 or when x is -2, it doesn't matter. Any value of x in this first region, if we go determine the first derivative, the sign will not change. It's either always positive or always negative. Now, I don't know which one it is in region 1. I have to find out, and I'm going to in a minute. But then I go to region 2, the same thing. Any value of x I choose that's in region 2, if I go find the first derivative for any value of x in here, it does not change. It's either always positive or negative. And the same thing for region 3. So here's what I do. I need to figure out what's going on inside the regions. So let's look at region 1. I want to see, for the values of x in region 1, whether the first derivative of this function is a positive or negative number. And all I have to do is figure it out for one value of x, because it's not going to change. So what you do, you just pick one value of x in region 1. I'll just say, I'm going to look at what happens when x is -2. And what I do is, I actually go take my derivative equation and I plug in -2 for x, and I see what it equals. So here's my derivative equation. I'm going to plug in -2 for x. So that becomes a calculation. Negative 2 squared is 4. Negative 18 times negative 2 is plus 36 minus 30. This right here is 48. Want to make sure I'm not messing up on my math. Let me check my notes. I don't want to make a mistake in these videos and then have to go back and correct it. Let me get my notes. Yeah, see, I think I made a mistake. Oh, I'm okay. Sorry. 48 plus 36 minus 30. You know what? I don't even necessarily care what the number is. Obviously, it's going to be 36 minus 36. 6, I guess I can figure it out. What I really care about, that this is a positive number. I've now determined, I chose a value of x in my first region. I plugged it into the first derivative, and I found out it's positive. That means I go up here and I say, for all the values of x in this region, my function, the first derivative is positive. You know what that means? That means in this first region, sometimes I draw it in here, my function is increasing in this first region. How would I know that? Because I know the first derivative is positive. A positive first derivative means your function's increasing. It's like a positive slope, it's going up. I have now just determined in this area of the graph, my function, it's going up. What's going on in region 2? You do the same thing. I choose a value of x somewhere in region 2, and I go plug that into my first derivative and see if it's positive or negative. I'm going to choose 0, just because it's easy to do math when you have 0. So in this case, first derivative when x is 0, pretty straightforward. This is going to be 0, this is 0. I end up equals negative 30. The second region, I now say the first derivative is negative. You know what a negative first derivative tells me about the function? It's decreasing. The function is always going down. So I actually go in here and I sort of draw a function going down. Now look, on either side of my critical point, I've determined if the first derivative is positive or negative. On the left-hand side, a positive first derivative, which means my function is increasing. On this side, a negative first derivative decreasing. Obviously, what's happening here? Obviously, minus 1, this critical point, is a maximum. Here's my second critical point. What's going on here? Well, I know the function's decreasing, but now I have to look and see what's going on in region 3. So region 3, I'm going to choose a value of x in region 3. This is 2.5, so I'll just choose 3. So once again, I choose a point in here. I'm going to go find out what the first derivative is at that point. And really, all I care about is if it's a positive or negative number. That's really the important thing. So now I plug in 3 into here. 12 times 3 squared minus 18 times 3 minus 30. 12 times 9 minus 54 minus 30. 12 times 9 is 90 plus 18 was at 108 minus I don't even care about the exact number. You know what? All I care about is, obviously, this is a positive number. Region 3 is a positive region, which means the function's increasing. Think of it like this. So what's going on at this critical point? Obviously, it's a minimum. So I can now say I have a maximum when x is -1, and I have a minimum when x is 5/2. So once again, quick review. We've done a lot of stuff. Very first thing we did, we wanted to find the critical points, the values of x. That's the critical points. How do we do that? You take the first derivative set equal to 0. When we did that, we found we had two critical points, -1 and 5/2. Now at that point, I don't know whether these are the maxes or mins or what's going on here. So how do I determine that? Well, you create this chart, and what we're really doing is analyzing what's going on at their critical points, or we're really looking at what's going on either side of their critical points. So we do this little chart here, this little graph where we mark our critical points, which breaks it up into regions. And then you look at each region and you ask yourself, or you figure out, what's the first derivative in each of these regions? Is it positive or negative? It's not going to change inside the region. So all you do is, we grabbed one point, one value of x in each region, calculated the first derivative. In this first region, we found out first derivative is positive. What does that mean? Increasing function. We went to the second region. First derivative is negative. That means function's decreasing. We go to the third region. We found out the first derivative is positive, increasing function. Therefore, we realize we have a maximum when x is -1 and minimum when x is 5/2. Now that we've found this, these other questions we were asking, look at the questions we started with. What are the critical points? Okay, we did that. For those critical points, what are they, maxes or mins? We've now determined that, and it said find the values of x. Now they said find the intervals where the function is either increasing or decreasing. Well, that's pretty easy to do. Because now if you look at this, you can sort of look at this little graph here. What's going on? As x is between -infinity and -1, what's the function doing? It's increasing. And then from -1 to 5/2, the function's decreasing. Then from 5/2 to infinity, it's increasing. So actually, let me try and write that where you can see it. If I sort of, let me just do this, where you can see the sort of the picture. So where's the function increasing? I'm going to write this as intervals. Region 1 is an increasing region, function's going up, and it goes from -infinity to -1. So this is an increasing region, but there's also, look at region 3, the function's also increasing there. So I have a second interval, which starts at 5/2, and it goes to infinity. So there are two regions where the function is increasing. So where is the function decreasing? Region 2, right here in the middle, this one section. And it goes from -1 to 5/2. So once you find your critical points and you find out whether they're maxes or mins, the increasing, decreasing functions, it's very simple. Now let me do this fourth point that I said in here. Find the value of f of x of the max or min. So in other words, when I found the max or min, I just found the value of x. Sometimes that's all they ask for. But there will be times when they actually want to know what the value of the function is at the max and the min. In other words, what I really want to do now is, at that point, to get both the x and the y. So I know the x is -1. I don't know the y. And for the minimum, I know it's 5/2. So I want to find the y. So how do I find this y? And this is key. You have to go back to the original function. Don't go back to the derivative. You go back, way back to the original function. Start of the problem. And I'm going to plug in my value of x. So if I want to know the value of y, or the value of the function, it's f of -1. And here is my function. So you plug in -1 for x. 4 times -1 cubed minus 9, -1 squared, minus 30 times -1 plus 25. So this is -1, -4, -1 squared is 1, minus 9, plus 30, plus 25. 55 minus 13 looks like 42. So it looks like when x is -1, y, or the function is 42. Now actually, I didn't do this in advance, I don't think. And actually, doing 5/2 could be sort of messy. So what I'm not going to take the time to do is, basically, I would now, for my minimum point, I would take my original function and put in 5/2. And that's pretty messy. So I apologize, but I'm not going to take the time to do this now because I want to finish this problem. Now here's what I want to do. Last thing. I actually took a computer program and I sort of printed out. Here's the function we started with. 4x cubed minus x squared minus x. There's an online program where you can graph it. And here's the graph of it. Now if we look, we said what are the critical points? We said the critical points were -1 and 5/2, which is 2.5. Here's 3. So here's 5/2. And we said at -1 you have a maximum. Matter of fact, we said it was 42. So here's the maximum. -1, 42. The minimum, here's our other critical point, 5/2. Here's the minimum. And if we finish that calculation, it looks like we would have gotten a -40 something. So the point is, there's the max, and there's the min. This confirms what we did mathematically. Obviously, if you were given this graph at the beginning, you would have said, here's the max, here's the min, and you're done. But instead, what you were given was this equation, and you were asked to find the maxes and the mins. As a matter of fact, in a little bit, the problem's going to be, they're going to give you this function, and they're going to say, figure a bunch of things out, and then go ahead and try and sketch the graph of this function. So we're going to learn lots of things about this function, and once we learn everything, we're going to try and create a graph. So some of the key things we have to learn are like the max and the min. Knowing these 2 points would be very important if we were trying to sketch this graph. All right, so this is one of the big things we do with calculus and the first derivative. You take a function, and the first derivative can tell us how to find our critical points, which are usually either maximums or minimums. Now in the next video, I will do another problem where we work through this thing the same way, just to give you a little more exposure. And that'll be the next video.